Good morning, everyone. Today, I would like to cover the chapter curves, which is very important in surveying. Till now, we have discussed tachymetric surveying, trigonometrical leveling surveying, and now in this class, I am going to cover some portion of curves. So, we will learn what is a curve, what is the designation of a curve, how the curves are important for civil engineers, how they play a vital role in civil engineering, etc. We will learn, and what are the different types of curves, how we will construct the curves in real field. These are the things we are going to learn. So let us start today's class. So our objectives in this class is to cover, we have to know what is a curve, then we have to understand the uses of curves in civil engineering, means where the curves are useful for civil engineer, and then we have to go for types of curves, what are the different types of curves, where we will use these types of curves and all, and then we learn different terms involved in curves. So these are the objectives we will learn now. Let us understand what is a curve. Whether all the roads are straight? No, not it is possible. Roads cannot be straight for a longer distance. We have to provide some curve. We have to observe uh, where it has to be provided. Suppose if we are going to provide a left side curve or right side curve, we have to observe the slope also, and what slope we have to give to the curve and all. So these are all the things we need to look at. Along with this, the curves are most important not only in a road, and they are also important in railway tracks. They plays a vital role in railway engineering because we cannot provide a direct curve in railways. We cannot directly turn the track. So we have to provide a smooth curve so that the train may not slip from the track. So we need to take a lot of care in providing curves for railway tracks. These are all the things we are going to cover. So the major importance of curves in civil engineering is in the construction of roads and railway tracks. So these are the things we are going to learn. So curves are generally used in highways and railways where it is necessary to change the direction of motion. So just now we have discussed when a road is, when we have to take a turn, we have to change the direction. In such cases, we are going to provide curves. Now let us see what are the different types of curves. We have circular curves, parabolic curves, spiral curves, but in our diploma advanced surveying subject, we have circular curves only. We don't have parabolic curves and spiral curves, which we will cover in BTech. So for now, we are going to cover circular curves. So there is a classification of circular curves. These circular curves can be classified as simple curves, compound curves, and reverse curves. These are the classification of circular curves. Now we will discuss what is a circular curve, what are the different types, what is simple curve, what is compound curve, what is reverse curve, and all. Now this is the classification of circular curves. Let us see what is a simple curve. A simple curve is a curve arc having arc connecting two straight lines. So here we are having two straight lines, AB and BC. So it is T1, T2 is an arc. It is a single arc of a circle. is a single arc of a circle having radius r, which is making an angle phi with the center. So this is called simple circular curve, or we can simply call simple curve. It is tangential to both the straight lines. Now if we observe the diagram at T1, it is the line AB is tangential to the curve at T1. Similarly, at T2, the line BC is tangential to the curve. So this is called a simple circular curve or simple curve. This diagram shows a compound curve, an example for compound curve. Here we can observe there are two arcs. This is first one, then this is second one. We have differentiated the two arcs with different colors so that we will understand easy. Here we have two or more arcs. In compound curve we have two or more arcs. I have shown an example for two arcs. The compound curve may have more arcs than two of different radius lying on the same side of the common tangent. Suppose if we say this is the common tangent, both the curves lies in the same side of common tangent, and these two curves are having different radius. The radius of this curve, red curve, is r1. The radius of this curve is r2. So here we are having two or more curves with different radius, which is called compound curve. Then the third type of curve is reverse curve. It consists of two arcs of different radii or same radii. But if we observe, the common tangent will have two arcs on either side. This is reverse curve. So let us say this is common tangent. We have two curves this side and this side. So this is called reverse curve. It consists of two arcs of same radius, or the radius may be different. The centers of opposite side of a common tangent. Common tangent will have two curves on either side. So this is called a reverse curve. We will give some definitions. We will learn some definitions, and we will give some common notations for the curve, which are common till the end of the chapter. This is a starting point of the road, or we can say a straight. T1 is starting point of the curve, which is known as point of commencement. So PC indicates point of commencement. Point of commencement means the point where the curve starts. Here we have T2. T2 means it is point of tangency, where the curve ends, or the last point of the curve can be called as point of tangency, or the point at which curve ends. Here we have delta. Delta is a deflection angle. Delta is the angle by which the straight AB is deflected here. So delta is deflection angle. There is a relation between delta and phi. Phi is the included angle here. So this is delta plus phi will be equal to 180 degrees. O is the center of the arc. Let us take a simple circular curve of center O. O is the center. R is the radius of the circular arc. O is the center of mid-ordinate. Let us say T1, O, T2 is the mid-ordinate. Sorry, this is a long chord. This is T1, O, T2 is long chord for this curve. This is the possible long chord. So O is the D is the center of long chord, whereas C is the center of the curve. These are the different notations, and we will understand very clearly while doing the problems. So here some of the definitions are given. We have to go through this definition for better understanding. The first one is back tangent. Tangent at T1 is called back tangent. Or we can say that the tangent AT1 previous to the curve is called back tangent or first tangent. In the diagram, this line indicates back tangent. Next, a forward tangent. Tangent at T2 or tangent T2B following the curve is called forward tangent or second tangent. In this diagram, this line indicates forward tangent or second tangent. Then point of intersection. Here we are having two straights which are intersecting at a vertex. This is vertex V. This is called point of intersection. If the two tangents AT1 and BT2 are produced, they will meet in a point called the point of intersection, VI, or it can be called as vertex V. In the diagram, we can observe that two tangents AB and this line are intersecting at a point. Let us say this is BB are intersecting at a point V. So V is the intersection point. Now we'll have point of curve. It is the beginning of the curve where the alignment changes from tangent to a curve. It is actually not point of curve, this is point of commencement. Point of commencement means the point at which the curve starts. So T1 can be called as point of commencement. And then we have another point T2. T2 is nothing but point of tangency where the curve ends. It is the end point of the curve where the alignment changes from a curve to the tangent. So this is point of tangency. You can see in the diagram also. This is point of tangency T2. T1 is point of commencement. Then we'll have intersection angle. The angle V between the tangent AB produced and VB is called the intersection angle delta on the external deflection angle between the two tangents. So we have two tangents here, and this is the deflection angle between the two tangents, which is called intersection angle delta. And we have tangent distance. It is the distance between point of commencement to the point of intersection. So we have point of commencement here, and this is point of intersection. This distance is called tangent distance. And we have external distance. It is the distance from the midpoint of the curve to the point of intersection. We have midpoint here and the point of intersection. This is called external distance E. Then we have length of the curve. It is the total length of the curve from point of commencement to the point of tangency. So we have to measure along the curve. We cannot measure along the long chord. If you measure along the long chord, it is called length of long chord. It is different from length of the curve. If we want to measure length of the curve, we have to measure along the curve. It may start at a point of commencement and it will end at point of tangency. If you observe these two things, they will start and end at same points. But we have to measure along the curve in this case, but we have to measure along the chord in this case. And we have mid-ordinate. It is the ordinate from the midpoint of the long chord. We have long chord and the midpoint of the long chord can be calculated. It is the ordinate at the midpoint of the long chord. It is called mid-ordinate of the curve. and we have normal chord. The chord between any two successive regular stations on a curve is called normal chord. Subchord is any chord shorter than normal chord. Then right hand curve, left hand curve. The curve deflects to the right side of the right side, the direction of the progress of the survey. It is called a right hand curve. If the curve deflects to the left side of the direction of the progression of survey, it is called left hand curve. So simply we can say that the curve turns left, it is called a left hand curve. The curve turns right, it is called right hand curve. So till now we have understood that what is a curve and what are the designations of curve. So and now I'm going to explain how we designate a curve, and we will solve some simple problems on this. Designation of a curve is done by two ways. It is done by its radius and it is done by its degree of curvature. We can say 300-meter radius, 300-meter curve means it is designated by radius. We can say 6-degree curve, 5-degree curve, 4-degree curve means it is designated by degree also. So these are two methods to designate a curve. First method is by designating by radius, and the second one is designating by degree of curvature. What is degree of curvature? According to the arc definition, it is the central angle D subtended by 30-meter length of arc at its center. Suppose if the arc is 30-meter length, then we have to measure central angle subtended. This is called degree of curve. According to the chord definitions, it is the central angle subtended by 30-meter length of chord at its center. So we can derive the relation between degree of curve and radius of curve. According to the arc definition, it is arc subtended by 30-meter length of chord. So 30 is to 2 pi r is d degrees is to 360 degrees. If we simplify this, we will get r is equal to 360 by d into 30 by 2 pi. Therefore, it is 1718.9 by d. So the definition, the relation between r and d is r is equal to 1718.9 by d, where r is the radius of the curve, d is the degree of curve. The radius of 1 degree curve is 1718.9 meters, because for 1 degree curve d will be 1, r is equal to 1718.9 meters. In this way we will measure a radius of curve for a given degree of curve. Suppose if any problem degree of curve is not given, radius of the curve is given, we can calculate from this equation. According to the chord definition, let AB be the length of the chord, and let 30 meters, let D is the degree of curve, and subtended by chord at center from O. From the triangle OBC, sin D by 2 is equal to AC by 2A, because sin means opposite side by hypotenuse, which is 15 by R. Therefore, R is equal to 15 by sin D by 2. When D is small, sin D by 2 can be written as D by 2 radians. R is equal to 15 by sin D by 2. So D by 2 can be written as sin D by 2 can be written as D by 2 for small angles. If you convert in radians, we will get into pi by 180. In simplifying this, we will get 1718.9 by D. Again, the same value which already we got in the previous calculations. So here also we got R is equal to 1718.9 by D degrees. Now We will see what are the elements of simple circular curve. We have different elements in a simple circular curve. The first one is length of the curve. Length of the curve is like this curve length. This is nothing but r phi. So r theta, r delta. So this intersection angle is delta. Therefore, this is r into delta. If you convert this value into radians, we will get pi r delta by 180 degrees. Then we will have tangent length. Tangent length is nothing but T1, V or T2, V T2. Both are same, which is OT1 into tan alpha, tan delta by 2. This is R tan delta by 2. R tan delta by 2. Length of long chord is nothing but T1, T2, which is 2 times the OT1 sine delta by 2. From this triangle, we will get OT1 value. If you want to calculate the total length of chord, long chord, we have to multiply it with 2 because we have two halves of long chord here. We are measuring this half and we are multiplying with 2. So here we'll get length of long chord L is equal to T1 T2, which is 2 times OT1 sine delta by 2, which can be written as OT1 is nothing but radius of a simple circular curve. So we will get 2r sine delta by 2. And then apex distance or external distance E, which is nothing but CV minus CV, which is VO minus CO. On simplifying, we will get R into secant alpha by 2, secant delta by 2 minus R. And then we have mid ordinate, which is CD. CD is nothing but CO minus DO. CO value is nothing but radius of the curve, and DO is R cos by 2, R cos delta by 2 already calculated. On simplifying, we will get R into 1 minus cos pi by 2. We will again look into these elements. We will directly go into the formulas because these formulas are very important in calculations and numerical solving also. So length of the curve is pi r delta by 180 degrees. Tangent length is r tan delta by 2. Length of the long chord is 2r sine delta by 2. Apex distance is r secant delta by 2 minus r. Mid ordinate is r into 1 minus cos delta by 2. These are 5 very important elements of simple circular. Now we will solve some of the problems so that we will get more clarity. Let us see the first problem. Two strides meet at an angle of 150 degrees at a Chinese 35 plus 12.8 meters. They are to be connected by a circular curve of radius 300 meters. Determine degree of curve, length of curve, child ages of the first and last points on the curve, apex distance, versed sine of the curve, and length of long curve. One chain length is 20 meters. Here he has given 35 plus 12.8 meters. It means 35 chains plus 12.8 meters. One chain length is 20 meters. Therefore, 35 chains length will be 35 into 20 meters. Then we have to add this 12.8 meters to that to get the actual chainage. It is denoted by 35 plus 12.8 meters. Radius of the curve is 300 meters given. Intersection angle is 150 meters, 150 degrees. Deflection angle is 180 minus 150 degrees. We will get 30 degrees. Degree of curve is 1145.92 by R, which is 3.82 degrees. This is the formula already we have derived, and we can substitute here. We will get to 3.82 degrees. Tangent distance is R tan delta by 2. We have to know these formulas before solving any problem. We have 5 elements, and for 5 elements we have to know the formulas. For tangent distance, the formula is R tan delta by 2. This is 300 tan 15 degrees. Most of the people commit a mistake here that they will directly substitute intersection angle in case of delta. But delta is different from intersection angle. Delta is the deflection angle, which is 30 degrees. So we will get tangent distance as 80.38 meters. Then length of the curve is r delta into pi by 180. We have already calculated delta value 30 degrees. Remaining all things is given in the problem itself. If you calculate, you will get 157.08 meters. Chains of intersection is given as 35 chains plus 12.8 meters, which means 35 into 20 plus 12.8 meters. Less tangent length. Apex distance is r into secant delta by 2 minus 1. We have to substitute all these values. We will get 10.222 meters. Length of long chord is 2r delta sine delta by 2. We will get 2 into 300 sine 50 degrees. So which is 155.291. For solving this type of problems, you must remember the formulas for elements of simple circular curve. Otherwise, it is very difficult to remember, difficult to solve. So after solving different elements of simple circular curve, now we will learn what are various methods for setting simple circular curves. So the setting of simple circular curve means we have to set the simple circular curve in the field. We have different methods. We can categorize the basic methods as linear methods and angular methods. By the name itself, it suggests linear means we will take some linear measurements like length, channel, etc. For angular measurements, we will take angles also. These are different linear methods of curve setting. We have offsets from long chord, offsets from tangents, offsets from chords produced, successive bisection of arcs or chords. These are 4 different linear methods of curve setting. Offsets from long chord, offsets from tangents, offsets from chords produced, successive bisection of arcs. Again, we have 2 methods here: offsets of tangent, perpendicular offsets, and radial offsets. So we have again 2 methods in offsets from tangent method. We have perpendicular offsets method and radial offsets method. We will discuss all the methods in detail, and we will solve some of the problems related to these methods. Now, angular methods of curve setting. We have 2 different methods: two-theodolite method and Rankine's method of deflection angles. These are the 2 methods we will use for setting curves by using angles. So, as discussed earlier, you can set a simple circular curves by 2 methods: methods involving chain and tape, and methods involving angular measurements also. In the first type, we have offsets from long chord, successive bisection of arcs, offsets from tangent. We have 2 methods here also: long offsets from radial offsets and perpendicular offsets. Then we'll have offsets from chords produced. We have discussed what are the angular measurements methods. We have Rankine's deflection angle measurements and two-theodolite method. Now we will discuss the first method of setting out curves by offsets from long chord. This diagram represents a simple circular curve. We know the notations. T1 is the point of commencement, T2 is the point of tangency, O is the center of curve, R is the radius of the curve, D is center of long chord, D is apex distance. This is apex distance. This is mid-ordinate distance. Now, this method is called setting of curves by offset from long chord. We are setting offsets from long chord. Here the long chord is T1, D, T2. we need to measure, we need to set a long chord, we need to set a offset from long chord. So for this purpose, I took a point F on long chord, which is at a, let us say at a distance of x meters from center of the long chord. Again, I am repeating. I have selected a point F on the long chord, which is at distance of x meters from center of the long chord D. Then I projected this point on the curve vertically, parallel to the mid-ordinate. So this is the projection. Let us say this is ordinate distance OX. This is what we have to calculate. If we observe, it forms a triangle here. This is E. If you project, if you horizontally project this E, we'll have E naught. So this we created a rectangle triangle here. In a right angle triangle, we can apply Pythagoras theorem. Setting out a curve by ordinates from long chords. Let R is the R radius of the curve. O0 is the mid-ordinate. OX is the ordinate at a distance x from midpoint of the curve. T1 and T2 are tangent points. L is the long chord actually measured on the ground. From the right angle triangle OT1D, OT1 square is equal to T1D whole square plus TO square. OT1 is nothing but radius of the curve. Therefore, R square is equal to L by 2 whole square plus CO minus CD whole square, which is R minus O whole square. On simplifying this, we will get R minus O is equal to under root R square minus L by 2 whole square, which is nothing but, if you take R as common, R from R to the right side, we will get O0 is equal to R minus under root R square minus L by 2 whole square. This is the formula for O0. To calculate the ordinate OX to any point E, draw the line E1 parallel to the long chord T1, T2. Just now I have explained. Join EO to cut the long chord at Z. Therefore, OX is equal to EF, which is nothing but E1D. E1D is E1O minus DO. So here we will get EO square minus E1 square minus CO CD, which is CO minus CD. This is R minus R square minus X square under root minus R minus O0. This is the formula for OX. For different distances of X, we have to substitute. We have to calculate different ordinates. Suppose the long chord length is 100 meters. We have to divide it into two parts. If we divide it into two parts, we will get X as a 0, 10, 20, 30, 40. Because the total length is 50 meters, you have to divide it into 5 parts based on Peckinpah. We have to measure the ordinate distances. And then X value is substituted substituted based on Peckinpah. To set out the curve, long chord is divided into an even number of equal parts. Offsets calculated from the equation 1 and then set out at each of these points. Now we can summarize this particular topic. We have discussed different methods of curve setting, along with setting out curves by ordinates from long chord. We have derived the equation for ordinates at midpoint of the curve, along with ordinates at different points from the center of the curve. There are the things which we have learned so far. And then we'll move to another method. So we have offsets from tangents method. This is the second method of setting a simple circular curve by chain and tape. Large radius curves with relatively small deflection angles can be set out by Cutting out from tangents method. So offsets may be two types, radial offsets or perpendicular offsets. Now we will discuss the radial offsets method. Let us say this is a simple circular curve. This diagram represents the takeout curve by radial offsets. Let us say this is a simple circular curve. T1 is the starting point, R is the radius. Let us say this is tangent, T1D is the tangent, OX is the ordinate from which it touches the curve. So from this, you can write that OX is the radial offset at a distance x from the tangent point T1. This is radial offset. So which is along the radius of the curve. Therefore, from this we can write OX is equal to R square plus X square minus R, which can be derived from right angle triangle again, which already explained previously. If R is the large there, X2 is equal to R plus OX. Neglecting OX square, we'll get OX is equal to setting out curve by perpendicular offsets. DE is equal to OX, which is offset perpendicular to the tangent. T1D is x1 measured along the tangent. Draw E1 parallel to the tangent. From triangle E1O, we have E1O minus T1 E1 whole square is equal to UI square minus E1E whole square, or R minus OX whole square is equal to R square minus X square. From this, if we simplify, we'll get OX value as R minus R square minus X square under root. For a given values of X, we have to substitute different X values here to get offsets. It may be 10 meter, 20 meter, 30 meter, etc. Depending upon the tangent length, we have to substitute X values to get OX. For different OX values, we'll draw on the tangent to get the simple circular curve. The corresponding expression of OX may be obtaining by the expanding term of R square minus X square. Thus, OX is equal to R minus R into R minus 1 minus X square by 2 R square minus X power 4 by 8 power alpha 4 is 1. Neglecting terms, we get some value. So we have learned how to set the perpendicular offsets and radial offsets in this class. And we have successive bisection of arcs. Here, the arc is successively bisected. So therefore, F is equal to R into 1 minus cos phi by 2, which we have known already. In the second bisection, we will have R into 1 minus cos phi by 4. It is same like R into 1 minus cos phi by 8 and so on. So like this, we will measure bisection of parts and we will substitute the values to get the final curve. The curve is divided into number of parts, normally 20 to 30 meter in length. Due to continuity in Chinese, we'll get subparts. One at the beginning and the other at the end of the curve. Offsets from card produced may be computed as below. So these are the formulas for offsets from card produced. O1 is equal to C1 square divided by 2R. O2 is C2 into C1 plus C2 by 2R. O3 is C3 into C2 plus C3 by 2R and so on. All the parts are except subparts are equal. This is the simple circular curve there, from which we have to measure all these things. For the last subpart, On is equal to Cn into Cn plus Cn minus 1 by 2R. So these are the different subparts produced. Locating the tangents T1 and T2 to out there changes. Calculate the length C for the first subpart so that the first part gives the full station. The zero mark at T1, Spread the chain along the first tangent to point A1 on it such that T1 A1 is equal to C is equal to length of first subcurve. With T1 as center and T2A as radius, swing the chain such that arc A1A is equal to calculated offset O1. So fix the point A on the curve. Spread the chain along T1A and pull it straight in the direction to B2 such that the zero of the chain as a and the distance ABT is equal to C, which is nothing but length of the normal curve. With zero end of the chain centered at A and A2 B2 as radius, bring the chain to a point B such that B2 B will be equal to O2, which is nothing but length of the second offset. Fix the point B on the curve. Now spread the chain along AB. Repeat the steps already explained before at point T1 until the point tangency is reached. All intermediate offsets will be equal to C1 square, C square by R, while other offsets will be equal to C square by 2R into C square into C plus C dash by 2R. The last point is so fixed must coincide with the point of tangency T2, fixed originally by measurements from the vertex. If the discrepancy is more, the curve should be reset. If the error is less, it should be distributed to the all points by moving them sideways by amount proportional to the square of their distance from the point T1. This method is mostly used in road surveys and it is very satisfactory in highway curves, especially used when a theodolite is not available. So from this we can understand how to set the curve by chain and tape using different methods like successive bisection of arcs, successive bisection of curve, and successive setting out the curve by coordinates from the cost footage. Till now we have discussed what is the curve and how we will designate curve. There are two types of designations. We can designate the curve by radius or degree of curve, and we have learned what are the different types of curves available. We have a simple circular curve, a compound curve, a reverse curve. We have derived the equations for elements of simple circular curve, and we have discussed methods like chain and tape, setting out the methods using chain and tape. So all these methods we have discussed and derived the formulas for offsets from long chord, offsets from tangents. So we have again two different methods: radial offset method and perpendicular offset method. For all these things we have derived formulas. I hope all these things are clear till now. And one more thing we have derived is the relation between radius of the curve and degree of the curve. So the relation is R is equal to 1718.9 by D. It is very important because it is useful in the upcoming methods like Rankine's diffraction angle method, where we will use this formula. If R is given, degree of curve is, if we ask to calculate degree of curve, we can use this formula. In some cases, the degree of curve will be given and we have to calculate R value. In such cases also it is useful. So with this, I want to close the session of curves. In the next class, we will continue the other methods remaining for setting of simple circular curves. I hope this class is very helpful and we will meet again in the next class. Thank you.